have already discussed the arrangement of resistors, that is the series arrangement and the parallel arrangement. We also know that there are simple rules for the calculation of equivalent resistance of such combination. Two resistors are said to be in series if only one of their endpoint is joined and if a third resistor is joined with the series combination of the two, and then all the three are said to be in series. Clearly, this can be extended to a series combination of any number of resistors. Two or more resistors are said to be in parallel when one end of all the resistors is joined together, and similarly the other ends are also joined together. Just like resistors, the cells can also be combined together in an electric circuit. Like resistors, we can replace a combination of cells by an equivalent cell in such circuits. We discuss the connection of cells in series and in parallel in this session. Let us consider the cells in series first. We can see from the figure that the two cells are connected in series where one terminal of the two cells is joined together, leaving the other terminal in either cell free. Here E1 and E2 are the EMFs of the two cells and R1 and R2 are their internal resistance respectively. An equivalent circuit is shown here with a new EMF and internal resistance value. Let us now find out the value of equivalent EMF and resistance here. Here if V of A, V of B and V of C are the potentials at points A, B and C, then the potential difference between the positive and negative terminal of the first cell is given as V of A minus V of B. We know that V of AB is E1 minus I R1 and V of BC is E2 minus I R2. Therefore, VAC is equal to V of A minus V of C, which can be replaced with the equation V of A minus V of B plus V of B minus V of C. Therefore, V of AC will be E1 plus E2 minus I times R1 plus R2. We can simplify the above equation as V of AC equals E equivalent minus I times R equivalent. That is, E equivalent will be E1 plus E2 and R equivalent will be R1 plus R2. Or we can say that we could replace the combination by a single cell between A and C of EMF E equivalent and internal resistance R equivalent. We had initially connected the negative electrodes of the first to the positive electrode of the second. If we connect the two negatives, then V of BC will be minus E1 minus IR2 and the equivalent EMF will be E equivalent is equal to E1 minus E2. Thus, we have obtained the equivalent EMF and resistance, and the rule for series combination can be extended to any number of cells, say n number of cells. We can conclude that the equivalent EMF of a series combination of n cells is just the sum of their individual EMFs, and the equivalent internal resistance of a series combination of n cell is just the sum of their internal resistances. Now, let us consider a parallel combination of the cells. Similar to the above case, the circuit is replaced by an equivalent circuit. Let I1 and I2 are the currents leaving the positive electrodes of the cells. We have I equals I1 plus I2. If V of B1 and V of B2 are the potentials at B1 and B2, then for the first cell, the potential difference across the terminals is given by V equals V of B1 minus V of B2. That is, V equals to E1 minus I1 R1. For the second cell, the potential difference is given by V equals V of B1 minus V of B2. That equals to E2 minus I2 R2. As we already mentioned, I equals I1 plus I2, and substituting for them, we get E1 minus V by R1 plus E2 minus V by R2. Or we can say that I equals E1 by R1 plus E2 by R2 minus V times 1 by R1 plus 1 by R2. The potential difference is given as E1 R2 plus E2 R1 by R1 plus R2 minus I times R1 R2 by R1 plus R2. Therefore, the equation can be rewritten as V equals E equivalent minus I times R equivalent, with the equivalent EMF as E equivalent equals E1 R2 plus E2 R1 divided by R1 plus R2, and the equivalent internal resistance as R equivalent equals R1 R2 by R1 plus R2. That is, if we can replace the combination by a single cell between the points B1 and B2 with EMF E equivalent and internal resistance R equivalent. Expressing the above equations in a similar way, 1 by R equivalent equals 1 by R1 plus 1 by R2, or E equivalent by R equivalent equals E1 by R1 plus E2 by R2. Consider that there are n cells of EMF E1, E2, etc. up to En and of internal resistance R1, R2, etc. up to Rn respectively that are connected in parallel. Then the combination is equivalent to a single cell of EMF E equivalent and internal resistance R equivalent. Such as, we can write 1 by R equivalent is equal to 1 by R1 plus 1 by R2 etc. up to 1 by Rn, or we can write as E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2 etc. up to En by Rn. Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.